And today I'm gonna talk about the asymptotic behaviors for the eigenfrequencies of the Maxwell equation in the presence of small deformations. The presentation covers three parts. Number one, perturbed domain as a motivation. The second part is about the Maxwell eigenfrequencies problem in the presence of small perturbations, notations, spaces, and the problem. And on the last part, I'm going to talk about the asymptotic formula for the eigenfrequencies using the Osborn's theorem. So there have been several works, interesting works on the problem of eigenvalues, changes under variation of the domain since the seminal formula of Adama. The works by Kato, Ozawa, Kozlov, Bruno and Ricci, and Mary and others. Many published papers study the asymptotic formula for the eigenvalues in such domains. We see here 4 pictures of a different domain with the smooth boundary. Here, the rapidly oscillating boundary. Here, a domain with imperfection, microscopic local periodic oscillation, and in the 4th picture, shape deformation. And this has a lot of application in biological and medical imagery and others. So here we derive the asymptotic formula, and our result is an ambitious tool for reconstructing the interface changes for an electromagnetic inclusion for measurement of model measurement of eigenvalues. So we assume that omega is a subset of R3 with a smooth boundary, and such that the distance between the inclusion, the boundary of the inclusion, and the big domain omega, the boundary of the big domain, is greater than a constant d0, positive constant d0. The background medium is occupied by the material of magnetic permeability 0 and the electric permittivity epsilon 0. The constitutive parameters of the inclusion D are mu1 and epsilon 1, and they are denoted by the expression 2, mu dx is given by this expression, and epsilon dx is given by expression 3, where epsilon 0, epsilon 1, d0, and mu1 are finite, non-null, and bounded by a constant. So we recall that to write a vector field, we can write a vector field as the sum of the tangential component with the normal component. Such that the tangential component is given by 4 and the normal component is given by 5. Here, mu is the normal vector field on the boundary. So we denote by capital L squared omega the space of L to omega power 3 of squares interval function hash S omega and L infinity omega. So we consider the special spaces of Maxwell equation. Hash curl omega is the set of the vectors on L to omega such that the curl of V belongs to L to omega. And hash tip omega is the set of vectors on L to omega such that the divergence in L to omega. Hash 0 curl is the space hash curl omega intersects mu cross V equal to 0 on the boundary. Hash tip 0 omega is the set of vector on hash tip omega such that the divergence of V equal to 0. Now we denote the Maxwell eigenfrequency problem, denoted by the system 7. We suppose that E0 omega 0 squared belongs to hash 0 curl omega intersects hash div 0 omega times R. Solution of the set where this is the eigenfrequency problem given by Nedelec, the electromagnetic problem. And we suppose that the boundary is under delta perturbation, the inclusion of the boundary. So the boundary of d delta is equal to the set of all the x tilde such that x tilde is equal to x plus delta hx nu x, where x is on the boundary of D. Here nu is the outnormal vector of D, and h is a function such that the norm is bounded by C0, a positive constant, and delta also is a positive small parameter. So the perturbed domain can be given by 9. The perturbed problem, eigenvalue problem, can give it by 9. So we can write the problem as follows, where 1 open mu0 curl E delta plus, here we means by plus the on the exterior of the domain omega slash D delta cross mu minus 1 open mu1 curl E delta minus time cross mu equal to 0 on the boundary, and also epsilon 0 E delta plus scalar mu minus epsilon 1 E delta minus scalar mu equal to 0 on the boundary. The well-known theorem, thanks to Cato, let the eigenvalue problem of the Maxwell equation 9 in the presence of the perturbation that we denote in the previous section. Then there exists an infinite number of real eigenvalues as follows. With a note by E0I and E0I, the expression 10. So the transmission condition along the underpass of the boundary is given by this by the system element. Now we will give an estimate for an associated boundary value problem until we introduce the Hilbert space x omega, x delta omega, z delta omega, which are respectively equipped with the norm generated by the following linear product. Here we change, we simplify the domain because we need it after. So we get this lemma for all v in z delta omega, the set of v on hash curl omega such that the divergence of epsilon dv equal to 0 and v cross mu equal to 0 on the boundary. We have the following inequality. So the integral of omega of 1 open mu delta curl v squared is between C1 v, the norm of v on z delta squared, and the C2 the norm of v power 2 on z delta omega, where C1 and C2 are constant and dependent of delta. We get this result using the variational formulation and the upper bounds and upper bounds. Now, to give the asymptotic formula for the eigenfrequency, we suppose that f on belongs to z delta omega, such that v delta satisfies the following Maxwell system: curl 1 open v delta d delta curl v delta equal to epsilon d delta f, and curl 1 open v d curl v0 equal to epsilon d f in omega with the boundary condition v delta cross mu equal to 0, and here v0 cross mu equal to 0 on the boundary. So we get this theorem. Let mu d delta epsilon d delta be given as in 2 and 3. Assume that we have the perturbation and let f on x delta omega. Then the problem 13 admits a unique solution V delta which converges to the solution of 14. That means this is have unique solution that converges on this on V0. And for sufficiently small delta, the following uniform estimate holds: V delta minus V0 on Z delta omega is less than or equal to a constant C multiplied by the square root of delta, where the constant C is independent of delta. Here too, we use the variational formulation and some upper bounds to get this estimation. And of course, the norm of on the space of the delta. Now, we suppose that Y is the set of f on x omega, such that f cross mu equal to 0 on the boundary, with the inner product on x omega. T delta from Y to Y, a linear operator given by T delta f equal to V delta. The system 13, where V delta is the unique solution to 13. We define T from Y to Y such that Tf equal to V0, where V0 is the unique solution of 14. So we have this lemma. The following properties hold: T delta and T are self-adjoint compact operators, and this is thanks to the choosing of the spaces Z delta and X delta. The next property is that lambda 0 equal to 1 open omega 0 squared and lambda delta equal to 1 open omega delta squared, where omega 0, omega delta are the eigenfrequencies of the Maxwell equation, system 7 and 9 in the first system, respectively, are exactly the eigenvalues of T0 and T delta, respectively, and this is evident. The third property is that T delta are collectively compact, such that T delta goes to T pointwise as delta approaches to 0. And this is thanks to the variational formulation and this lemma that we denote by this theorem. So now I will give a version of Osborne's theorem, modified version of Osborne's theorem, a paper written on 1975. Let Y be the theorem 3. I will give the reference on the final of the presentation. Let Y be the Hilbert space and assume that T from Y to Y, a compact self-adjoint linear operator along with a sequence of compact self-adjoint linear operator T delta, such that T delta is collectively compact and T delta pointwise to T, and delta goes to 0. So for root 0, a simple eigenvalues of the operator T with the associated eigenfunction mu0, we have this inequality. Rho 0 minus rho delta minus the inner product T minus T delta U0 U0 on Y is less than or equal to C multiplied by this expression. Also, we have this inequality. Now, from this lemma and this estimate and this lemma, we suppose that T E0 equal to lambda 0 E0 and T delta E0 equal to V tilde delta, notation here, T delta E0 is V delta. We assume that we have the distance between the boundary, the boundary of omega and the boundary of D is less than a constant D0. There exists eta positive constant, and there exists a constant C independent of delta, such that we have this inequality. Curl V tilde delta E minus lambda 0 E0 power E on L infinity of the boundary delta slash P plus the curl V tilde delta power I minus lambda 0 E0 I on L infinity boundary of D delta intersect D is less than C multiplied by delta power eta open 2, where C is independent of delta and dependent of this parameter. The proof of this lemma is complicated because we use another lemma which is in the scalar case, and we denoted on the vector case. So for the simplification, we don't denote the other lemma. Now, we conclude this theorem from Osborne's theorem, the lemma, this and this lemma, the Osborne theorem and this lemma, and this estimation, we can conclude the theorem, the next theorem. Let omega 0 is a sample eigenfrequency for the Maxwell equation. Then there exists a sample eigenfrequency of 9 denoted by omega delta, such that omega delta squared goes to omega 0 squared as delta goes to 0. And the asymptotic expansion is denoted as follows. Omega delta squared minus omega 0 squared is equal to expression 18, where gamma is independent of delta. Here we remark that omega delta can be written in terms of omega 0 power 2 delta and the profile function hash x. Now we assume that omega 0 is the eigenfrequency of multiplicity m greater than 2 associated to the basis eigenfunction E0 G, solving the problem, the first problem of Maxwell eigenfrequency. And then for delta small enough, there exists m eigenfrequency omega G delta counted according to their multiplicity, such that their associated eigenfunction E delta G solve the system 9 of the perturbative problem. The Osborne version for the multiple eigenfrequency is denoted by this inequality. Lambda 0 minus lambda delta bar over line lambda delta minus 1 open m multiplied by the sum from for G from 1 to m, the inner product T minus T delta E0G, E0G x omega is less than a constant multiplied by the norm of T minus T delta on the subset of Y, curl T minus lambda multiplied by the identity, where lambda delta is equal to 1 over m, the sum of G equal to 1 to m, where m is the multiplicity, lambda delta G. Moreover, we have this inequality. So now, as it is done for the sample eigenfrequency, we can denote the theorem for the multiple eigenfrequencies. So let omega 0 be an eigenfrequency of the problem of the first problem with multiplicity m greater than 2. For delta small enough, there exists m eigenfrequencies counted according to their multiplicity, for the Maxwell equation in presence of the perturbation that converge to omega 0 as delta approaches to 0. And we have the following asymptotic formula, where here gamma is a positive constant. This constant is given from this estimate. And we can remark that also here the multiple eigenfrequencies are dependent on the eigenfrequency where the domain in the absence of the perturbation, and on delta and the hash, the profile hash of the perturbation. So this result can be can use it to identify the or to detect the perturbation on the domain using a shape optimization and minimization So that's all, and this is some reference here. Amirat and Shishkin talk about the asymptotic, prove the asymptotic formula for the Laplacian domain with oscillating boundary. Here, an interesting work that uses the same Osborne theorem, but here he gives us the reconstruction using the shape optimization. Here Hadar also talk about an asymptotic and its application on the transmission eigenvalues with the thin coating. Here we use also the Osborne theorem. Kato Nazarov also talk about the asymptotic of eigenvalues, and the well-known paper of Osborne is given on this paper. So for further work, we will talk about how to identify or how to reconstruct the interface changes of an electromagnetic inclusion. I'm not a good programming or a good programming, so if there is someone who want to collaborate to make this to solve this problem, I invite to send me an email. So thank you for your